Hello chemistry classes and welcome to the review lesson. For those of you that do not have me, I'm Mr. Malum, just in case you don't know that. We're just going to give you a little review before the quiz today. And so far what we've been doing is kind of exploring the relationship between these variables. So for example, we've done the relationship between pressure and volume. That happens to be Boyle's law. We've done the relationship between temperature and volume. That happens to be Charles' law. We have looked at the relationship between volume and the amount of gas. That's Avogadro's law. And we have also looked at the relationship between pressure and temperature. That's Gay-Lussac's law. So obviously, there's a couple more to go. For example, we could compare the amount of gas to the pressure, and we could compare the amount of gas to the temperature, and so on. For those of you that are a little bit more organized in your thoughts and you don't necessarily like the visual picture and arrows, I could do the same information that I was just sharing with you in a table or a chart. I would highly recommend that you write this table or chart down somewhere because it will be useful. There's even some room to enter some other items. The four gas laws that we've talked about at this point in time are Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's. So what two variables are involved in Boyle's law? Your choices are pressure, volume, temperature, or the number or amount of particles. What type of relationship is Boyle's law? And the formula for Boyle's law looks something like this. P1 V1 equals P2 V2. If the pressure increases, the volume decreases. What two variables are involved in Charles' law? Here's one of the things important about Charles' law. You have to keep the temperature in kelvins. To change from Celsius to kelvins, you add 273. What type of relationship is Charles' law? And the formula for Charles' law is V1 over T1 equals V2 over T2. What variables are involved when we're looking at Avogadro's law? What type of relationship is Avogadro's law? What's the formula for Avogadro's law? Notice that when we have direct relationships, the formulas look very similar. For a direct relationship, in this case, if the volume goes up, the temperature goes up. In this case, if the number of particles goes up, the volume goes up. What are the two variables that are involved in Gay-Lussac's law? Well, Gay-Lussac deals with pressure and temperature. And once again, since this formula deals with temperature, the temperature always has to be in kelvins. It is a direct relationship. I'm going to do one sample problem for each one of these just so you guys can kind of see how those are done. And in order to do those sample problems, I'm just going to... Alright, so here we go. This is going to be a Boyle's law problem. This happens to be one of the problems that was in, that I had you do for the Edpuzzle videos. The reason I'm choosing to do this one is because for my classes, when I did it, only 58% of the people got the right answer, which I can already tell you the right answer is going to be 43.2, because that's what was on the Edpuzzle. Let's just go through this and make sure everybody knows what's going on and how to do it. So, the first number that I get to is 765 millimeters of mercury. Millimeters of mercury is a pressure, so the question is that my pressure 1 or my pressure 2? Typically, before the change, we call those our pressure before, and the volume 1 is the volume before. So as I keep reading, I get to this second thing, and it even says right here it's a volume of 23.5 liters. So I'm going to put that one in for my volume. So these are the two pressure and volumes before a change. And it even says in the problem, the pressure is changed to 500 and, I see that my pressure units are two different units, and that's going to be a problem. You always need your pressures. It doesn't matter what pressure unit it is, but they have to be the same. So 765 millimeters of mercury, I could change this to millimeters of mercury, or I could change this one to ATM. It does not matter which way you do it, but the two pressure units in the problem do have to be the same. I'm going to take 765 and I'm going to go through and do a conversion to change that into ATM. So if this is millimeters of mercury, then down here I need a pressure that would be millimeters of mercury. So 760 millimeters of mercury is 1 ATM. That's the conversion factor we got when we did our pressure conversion problems. So if I take 765 times 1 divided by 760, I get this answer. 1.00657. That's probably enough significant digits. ATM. I'm not going to round for significant digits until I'm completely done with the problem and I've done everything. I just want to make sure that I have enough that I don't have any rounding errors. So instead of this pressure, I'm going to use this, which actually they're the same thing, they just have different units. Now I can do the problem that was originally set up. So I'm going to take my pressure 1 times my volume 1, and that's going to be equal to my pressure 2, 500 or 0.548, times, well, V2 is what I don't know. That's the thing that I'm actually looking for in the problem, is whatever V2 is. So I need to figure out V2. Right now the V2 is stuck with the 540 or 0.548. So what I'm going to do is I'm going to divide both sides by 0.548. So I'm going to divide it on this side. I'm going to divide the same thing on that side. And in this case, this is just how algebra works out. What we get is the 0.548 here cancels the 0.548 here. So I now have something that says V2 equals this. All I got to do is punch that in on my handy dandy calculator and I should get an answer. So 1.00657 times 23.5. I can hit equals if you'd like, and then divide by 0.548. And like I said before, we already knew what the answer was. Looking at significant digits. That was 3 significant digits when I started the problem. That's 3 significant digits. That's 3 significant digits. So I'm going to have to round to 3 significant digits, and I get 43.2. My final answer was liters, because the ATM on the top and the ATM on the bottom are going to cancel. So my unit of liters is right there. Final answer. So if we're looking at a Charles Law problem, I'm going to do this in a very similar manner. I'm going to go through and kind of dissect the Charles Law problem. Notice the formula for Charles' Law looks a little bit different than Boyle's Law. This is what the direct relationship formulas look like. So when I'm reading the problem, the very first thing that I get to is 23.5 liters. That is going to be my volume. That's the volume before the change, which is why I'm putting it right there. And 15, yep, can't use Celsius in my problem. 15 degrees Celsius, all the temperatures always need to be in Kelvins. So I am going to do a little conversion here, where if I take that 15 degrees Celsius and add 273, I get this, 288. So my new Kelvin temperature is 288. So I'm going to take that and put it right up here for my temperature 1. As I'm going across, I get to another thing that's liters. This is the liters after the change. So that's going to be my volume 2. I'm looking for the temperature. So same thing, I'm going to go through and plug in my numbers. 23.5 over, might as well leave that there so people can see it. Well, the temperature is 288. Let's clone that. There we go. And that's going to equal my volume over whatever that second temperature is. So in this case, I don't have a really nice expression to work at, especially since T2 is in the denominator. I got to get that T2 out of the denominator. The easiest way that I know to do that is to do a little cross multiplication. So cross multiplication means I'm going to take these two numbers and multiply them. So the new expression that I get is going to be 288 Kelvin times 32.9. I'm just being really systematic and taking my time as I go through and solve these. And then if I'm cross multiplying, what I'm going to do is I'm going to go the other direction now. And when I cross multiply, I'm going to get the 23.5 times T2. And now this is a much nicer expression to work with, because this expression looks a lot like the Boyle's Law problem, where if I want to get T2 by itself now, all I got to do is divide both sides by that 23.5. If I do it on this side, just make sure that you do the same thing on the other side. That's how algebra works. When I do that, these are going to cancel out. So now I get something that says T2 is equal to this times this divided by that. So I'm going to punch those in on my calculator quick. So when I punch that in on my calculator, 288 times 32.9, I got this. I divide by 23.5, and my final answer for that ended up being 403.2. But that's Kelvin. I know that's Kelvin because when I look at my problem, my liters cancel with liters. So my only unit left is kelvins. It's the only thing that's left is that Kelvin unit right there. So it was 403.2 kelvins, which means to get it back to a Celsius temperature, I'm going to have to subtract 273. And when I do that, I get 130.2 as my final answer. Looking at significant digits, I got 3 significant digits here. Just for the record, when I did my calculation, I took this number and added 273. This became 3 significant digits, and 3 significant digits is the right value. So this is 3, this is 3, this is 3. My answer should be 3. So 130 would be my final answer that I would get. 130. The reason I chose to do this problem is because in my class I only had 19% of my students get that one right when we did the Edpuzzle. Alright guys, so an Avogadro's problem to review before you take the quiz. There's a lot going on in this problem. So if I look at it, this is the volume and N is the number of moles. So when I go through and I start kind of dissecting this problem apart, well, here I can clearly see that this is a volume. And if I keep going through, I get a new volume. But it doesn't look like anywhere in here that I know the number of moles. But we've done this now for a couple of months. If you know the grams of nitrogen, you can get to the number of moles. So if I have 25.0 grams of nitrogen, I would use a periodic table. Keep in mind it's N2. So when you find nitrogen on the periodic table, it's going to have a molar mass of 14 grams per mole. But that it's N2, so we have to double the 14. That's where you get the 28 from, because 14 plus 14 is 28. And then 1 mole will be on the bottom. Now, how did I know the 28 grams goes on the bottom? Because if you have grams on the top and grams on the bottom, those two things are going to cancel each other out. So if I take 25 divided by 28, I will have the number of moles that I'm starting with. All right. So using Avogadro's law, I'm going to plug in my volume, that's V1, over number of moles, and that is going to be equal to the volume over the number of moles. And N2 is the thing that I don't know. So once again, I got these ratios set up. I am going to use a system of cross multiplication. where I'm going to cross multiply. So as I cross multiply, I'm going to take 12 times my number of moles, and that is going to be equal to, well, now I got to cross multiply in the other direction, 83 times my N2. And once I do this, I'm just going to set it up where very similar to the other problems that we've done now. Divide that. Divide over on the other side. Divide both sides by 83. Divide this side by 83. That's going to get the N2 all by itself. We're going to get our 83s to cancel out here. Liters are going to cancel out here, which will leave me with number of moles. So take out my handy dandy trusty calculator. 12 times 0.892857 divided by 83. Once I have this answer, this is not my final answer, because up here it asks how many grams of nitrogen. This is moles of nitrogen. So just like what I did before where I did a conversion to go from grams to moles, now I'm going to do a conversion to go from moles to grams. So what I did was I took that number 0.1290 and I put that up on the top here. I'm going to use the same conversion factor that I used before. I'm going to put 1 mole on the bottom this time though and 28 on top. Why am I putting 1 mole on the bottom? Again, I want my units of moles to cancel out. So if I take 28 times 0.1290877, 3.61, yeah, looks like I get 3 sig digs. 3.61 grams of nitrogen would be my final answer. And finally, a review of a Gay-Lussac problem. 258 kPa. That's my pressure. 22 degrees Celsius. Not going to be able to use that. I already know that if I have a degree Celsius, I am going to have to add 273 to that. So when I add 273 to 22 degrees, I get 295. So 295 will be my starting temperature. I'm just going to go ahead and infinite clone that right now so I can use it later. What is the Celsius temperature if the pressure is 132? So, looks like I am solving for my temperature 2. I'm going to take my P1. My P1, got to be careful when you're doing the problems, really easy to make a mistake. And that is equal to over T1. So P1 over T1 equals P2 over T2. Looks like we're going to cross multiply again. So if we're going to cross multiply, that means I'm going to take 295 times 132, and that is going to be equal to 258 times my T2. Divide both sides by the 258. Divide both sides by the 258, so I'm going to divide that side, and I'm going to divide this side. And this is again, pressure can be any unit as long as the pressure on the top and the pressure on the bottom are the same. If you're being careful with your units at this point in time, you'd be like, oh yeah, my units for kPa are going to cancel out, and that's good because that way we know that the only unit that we have left is Kelvin. Over here, the 258 kPa and the 258 kPa will cancel out. So if I take out my handy dandy trusty calculator, 295 times 132, I like to hit enter, divided by 258. I am not done with the problem yet because this is a Kelvin temperature. And the problem said, what is the Celsius temperature? So, in order to go from this Kelvin temperature back into a Celsius temperature, I'm going to have to subtract 273. I'm just going to do that right on my calculator. And I got minus 122. Same thing as the last problem that we had that had temperatures like this. Remember when I add these two together, I got 295. That is 3 significant digits. This is 3 significant digits. This is 3 significant digits. So my final answer should have 3 significant digits. My final answer is negative 122 degrees Celsius. So hopefully you guys got enough information where you can do well on your quiz today. And that's my chemistry buddy. Look how much chemistry Oreo's learning while he's here. Woo! Good luck on your quiz.